Hello, Joseph. How are you?
I'm good. How are you?
Good, thanks. I'm putting up the project example. I will try to reorganize it a little better. I uploaded some files, right? I will add more to this, but these are the good projects that were done a year ago in this class. Okay, so let's download your lab. We'll go ahead and get started. Hopefully the others will join us. We'll talk about what we need to do today as far as GIL. Okay, so we're doing lab 12. Today we're going to work with GIL, multi-thread, and parallel processing. We're going to benchmark these programs and see how we can implement GIL into our code. So here's your lab. Okay, so for GIL, which stands for Global Interpreter Lock, we didn't really emphasize too much of this in our lecture. So I want to spend the time in this lab to kind of see how you can implement GIL. This allows you to prevent race conditions. Mostly this week, we talk about potential issues that we will come across in concurrent programming, and race condition is one of the area that we touch on. Ideally, I prefer that you do this lab in your Linux virtual machine. Now, if you use your IDE, you can do all the exercises except for the last one, as that library require. The library is the OS library that you're going to use on the last part, but because it's using fork, and fork is not a method that is accepted in Windows environment or other OSs. So it will work with Apple iOS, but you have to install other packages to run it. So I just want you to know that if you're using your IDE, you can work mostly through all the exercises, and I'll show you how you can do that, except for the last one. Okay, so for Global Interpreter Lock, as you know that some of the library that we have been using, even though it's written in Python, you do see some of the libraries is also available in C. So CPython is the original, the origination for your Global Interpreter Lock. So when you use tools that uses GIL, likely that it is C in the back. And at the beginning of the semester, we talked about using Python, where you would see that it is, we would use something similar where it's written in C. So in this, what you see, it is a mutex that protects the access of certain Python objects. So when you're using multi-thread, as we talked about how it's shared memory space, you want to be able to protect a certain memory allocation when the thread is using that space. So it's gonna not allow the others to be able to take over, and that would prevent the race condition. So that means that when you use this, your Python bytecodes is going to be executed. It prevents race condition because it allows the thread to access the data safely, as threads share memory. And so because we're using multi-thread, they are running concurrently or simultaneously. So that means that we need to think about how we would be able to control the shared data, as it is dependent in the algorithm. So this shows you how threads are racing to access the change of data. So let's think about that, right? Basically, the data is like, if you think about like a horse track or a racetrack, the data is where the finish line is. So all of these threads is going to try to reach the data location. to be able to pull the data as they are running at the same time. So an example of this is we would be able to implement GIL, and GIL is going to allow you to control who's accessing that data, or it's going to lock it or prevent other threads from accessing the same data at the same time. So for thread safety, we need to think about how the data is manipulated. Okay, so in a way where if all the threads are accessing the same data, how the change in the data, is that going to give us inaccurate data, or will it not interfere with the other threads? So you have to think about the sequence of your data access when you implemented your algorithm. And GIL was invented for CPython memory management, but not for thread safe. So that means that only one thread can be run at one time. And so to really prevent your race condition, we can only permit that particular thread to access the data, only one thread. Okay. It does not prevent a process from running in a different processor of the machine. So if you have multi-core, right, a different process can stem other threads, and those threads might be accessing the same area of your memory to be able to pull data. So GIL ultimately is going to only allow one thread to run once within the interpreter. So when you use it in Python, as Python uses the interpreter, it's going to allow only one thread. Okay. Now, this is also known as the interpreter level lock. So this lock prevents multi-threads once Python interprets the code, and so that converts to your bytecode. When other threads can access that same resource is when GIL is released. So that means that the lock is released. So we emphasize a lot about locking and be able to use that. A lock is not really a lock. In this one, we're going to talk about how GIL is going to protect that access for that thread at that one time. Once it's released, then the other threads will be able to access it. Okay. So here it talks a little bit about how you can implement that in Python. And in that, you would see that it would create your bytecode or the extension PYC or PYO. So when it executes that in your applications, you're going to see the file with the bytecode extension. So at any given line for the Python application, that would be interpreted to a single bytecode. And so when you use like an import statement at the beginning of your program, that is basically expanded into many bytecode, because when you import the library will be continuously used throughout your code. So therefore that import statement is expanded compared to maybe another statement where it's only going to be used in that one bytecode. So when you're looking at the GIL for the CPython interpreter, what you would see is that GIL needs to release it for every group of your bytecode instructions in order for other threads to be able to access it. So when you have a complex line of code that acts on a single bytecode, GIL will not be released for that period of time that that statement needs to run. So when you run a statement, when you apply the GIL, it's going to lock it, right? So it won't release until that statement is complete or that section is complete. And this works best on Unix or Linux-based system, as it is a way that we can implement GIL using pythread type block alias. So at the C level, it's going to use mutex T. And for the C function, it's going to look like this for the lock. Okay, even though that you see that the library we use is in Python. Okay. So for the C extension, you would see that it's gonna begin, right? So when it creates that lock, it's gonna allow one specific thread to be able to access it. And then when it released, you would see that it's gonna end the allow, right? So to block the IO operation for other threads to access your storage location, it's going to begin allow threads. And when it ends the allow thread, it's going to unblock it. That means it's going to release it for other access. Okay. And then we touch on race condition already. This is dependent on the sequence and the timing of uncontrollable events. So if your program is designed to have multi-threads and it's accessing the data, right? Maybe thread A is accessing the data before the essential threads, right? The critical sections, then you would have a race condition. Okay. Now the community talk about potentially maybe removing GIL, as GIL prevent you from having concurrent programming, because remember that when you apply GIL, only one thread can access that area. So the ultimate goal of concurrent programming is to be able to have multiple threads or to be able to achieve many things at the same time. So if they get rid of GIL, then they would fulfill more of the objective in concurrent programming. But there will be other concerns about how that can impact, right, the way Python program would be written without GIL, using multi-thread and parallel processing. So there is an ongoing debate. I think that there is a push for GIL to be removed from the community, but we will see how this is going to be, as there are some concern about removing GIL completely. Okay. So today we are going to work with concurrent and parallel. So to really differentiate this, and we touched on this before, in concurrency, it defines the problem where parallelism is really defining the implementation. So when you are delivering the solutions, if you're implementing threads, you're using asynchronous programming. And in the last program of this exercise, you're going to see that we are going to use forking. And so in that, what you would see is we would have concurrent programming compared to when we have multiprocess, that will be parallel, right? Parallelism. And we spent a couple of chapters on this. So in both processes and threads, what we see is that our programming language is scheduled to run, whether we would use the interpreter or the compiler or even using our OS. So the whole objective is to really think about how our performance would be to deliver your goal of your program or your solutions through programming. Like I mentioned before, if you missed this, I will demo this in my Linux virtual machine. Ideally, this lab should be used in Linux VM. If you run it on IDE, I will show you how you can do that for the first few exercises. The last exercise, the last part of the lab, you cannot achieve it without running it in Linux, as fork is only supported in Unix or Linux. Okay. So once I have my VirtualBox, I want to make sure that you know how to set up your settings. We call that we want to make sure our system settings, right? You can boot, you can increase your RAM if you like, and then make sure that we have multiprocessor. Otherwise, your parallel program is not effective if we're only using a single core. So before you boot your virtual machine, you need to make sure that you change your setting and then click start. Okay. So if you already booted, you have to shut it down and then change the setting. Otherwise, it would not be effective. It won't let you change it. See, I'm already on it, so it already gray out my processor setting. Okay. So The first step in the exercise is to boot up your Linux virtual machine. And if you don't have Ubuntu, you can download like Kali from their website and then be able to use it. It's pretty much the same as Debian. Okay, so in our Linux virtual machine, we are going to go ahead and log in. And we are going to open up the terminal by searching for terminal in OAuth like this. Okay, you've seen this before. So here I am in my terminal. I'm going to go ahead and create a new code file, which is going to be called threadbenchmark.py. So I can use nano to create my file. And just to look closer at what we're doing, we have seen this program before. As this program was discussed right at the beginning, like maybe the first 3 chapters where we touch on how to be able to use random. But in this case, we are going to use threading, and we are also going to use multiprocessing. Okay. I intended it for it to be one program, and then we can change up the program on how it's ran so you can see the difference between threading and multiprocessing and sequential. So we are going to use random. So we would import random. We are going to have multi-threads inside the program. So we would import threading, and in that we would use thread superclass. Then we would have multiprocessing module, and we would import process class and its method. Then we initialize our variable size to contain this value, and this is the number of random numbers that's going to be appended to your list, my list. So this is the group of values that it's going to randomize and add it to your list. We are going to create 2 threads. So we would have a variable that stores the number 2, which we would use in the later part of our code. So in the next part, we would have a for loop, and we would use a for range to be able to append multiple things to our list. And here we would pass the initial value, which is your 0 and to 2. So we are going to generate it for 2 threads. And as each of them run or execute, it's going to add the value to our container, which is the list. Then we would define our function. So you would have the first function called func, and we would pass count and mylist, which stores what had been appended in the last loop. And so for the count, we would then use that as a value as your counter, right, to be able to loop. So we would have another for range, and we would then use the append method to append that random numbers to our list. So we would pass the random method. So number 1, generate the random value. Number 2 would then use that to pass it within the append method to add it to our list. So the first loop here is going to be for our threads to be able to add to the container. The second loop here is to actually append the random value. Remember that when we talked about in our lecture, we need to think about how we handle the data structure in the Python program, where you would have a container that would store your threads, and then you would have another container, or you would use that container to be able to control how you would access the data or the value for your program. Then we would have a multi-thread function. This is going to be specifically aimed for thread creation. Then you would have a jobs list, and it is a blank list, and we would then add or append to that list. So for our for loop, we would use a for range, and we would start at 0 and we would finish at 2 because we declare threads as 2. And to create a thread, we would have an object, right? So that means I can reuse that object as I loop. So here I would have a thread object, and this is instantiated for thread. So the target is going to be the function that I define, which is func, and the argument size is going to be the size. And for my list, it's going to be the index for each of the lists. So as it loops, right, it's going to be able to create the thread for the first and the second thread, and append it to the container. Then we would use that container and be able to loop through and start each of the thread and then join each of the thread. We talked about start and join before. Then we have a third function called simple. The reason why we implemented this is that we want to use the same program 3 ways. Number one, we're going to use the simple method to run it as a sequential program. So the simple function here simply is we are going to implement a loop, and it's going to loop through for each of our thread. And as it loops, it's going to call on the func function, right? And we're going to pass the size in my list. So this is going to allow us to do the sequential piece in this program. Even though you have all this extra code, right? So when you call on this function at the end in your main, then it's only going to execute this while calling the other function. Then we would have a multiprocess function, and here you would create processes container, which is a list, similar to what you've seen with the threads, right? But in this one, we're going to implement our for range. Recall that each of the process, you can have multi-threads, right? And you can have many processes. So what we're capitalizing is we are capitalizing on the multi-threads along with the multi-processes in this program. So when you write this function, you have a container that stores the processes, and then we would loop through our multiple threads, which is 2, right? We start at 0, we're going to go to 2, and you can have more than 2, of course. Then we create an object called P, and this object is going to be for process. So we instantiate it for the process class. We're going to target the func, very similar to what you've seen in the threads. And our arguments is going to be size and my list index. And we're going to append, right, as we look through the content of our project into our list container. And we would use a loop to start each of the process and join each of the process. Okay, so this part is really for the multi-processes using threads. Okay, so instead of writing only the multi-processes program or only multi-thread program, we can also combine both. Then we would have a main section. So you would say if namespace is main, right, we would call the function. So we can start with the specific function call, and that way we can time it. Okay. What I did was, for me, I want to confirm the program is done. The one that I uploaded didn't have this. So if you add that one line where it says print done, right, so you know that when it's complete, but it doesn't really matter, right? We are not really doing much with the output on this part, but I just want to confirm that it's finished. So you can add that print line. So once I have my program, then I would save by pressing Control X and then Y for yes and press enter. Okay. So with this program, what we're going to do is, if you're using Linux, then you can still just use the time command. And we talked about this in the second week or the third week. Okay. Now, if you don't use Linux, this is what you do. Oh, what was it? part A? Okay. So if you don't use Linux and if you use your IDE on this, you need to import time it. Okay, you have to add that line. Then you need to start and stop the clock, right? We've seen this in many examples already. By this time, you should know how to do this. Okay, so I just want to re-emphasize that if you use your IDE, you need to import time it. And then in your main, because we're calling the function, you want to start the clock right before the function call. So I have a variable called start time. And I would use the time it module. So I would declare it as a default timer from time it library. So when it prints out, it's going to show you like your default system time. And then we want to print, right, your start time. Then we call the function. So we start the clock here at the beginning of main before the function call. Then after it prints done, I want to show the execution time. So I would do a print execution time, and I would take the default timer and I would subtract the start time. Okay. And so it's going to tell you, right, how long it's going to take for that to run. So let me clear this. I'm going to show you an IDE and then we're going to run it in Linux. Okay. So if you're using your IDE, you simply import time it, create a variable that activate your timer, show your system time at the start of the program or the execution, and then print out the difference. All right, then when we run this, okay, so it tells me that in here, right, this is the start time for my system. That's the default timer. And then to execute this, right, and I'm on my 8 core in my IDE. So it shows me that is, sorry, let me double check my function call here. Yeah, so when you do the multi-threaded one, it would be 3.04 second. So that's how you can use time it with the existing program. So coming back to the lab now, right? We leave this uncommented, so we want to run it as a multi-thread. And if you're using Linux, coming here, you simply just do a time command and then call on Python 3 and then run your file name, thread benchmark.py. So now the time module in Linux, it is a little bit more detailed than what you see using timeit library in the IDE. It tells me that the real time is 3.483 seconds. And recall that my virtual machine is only 4 core. I'm using half of my number of cores. So that's why when I ran it on the IDE, it's slightly faster. And then for the user, right, because your operating system have 2 modes. There's the user mode, and then there's your system mode, and then the real time, right? So real time is going to be slightly higher. So from the user mode, you would have it at 3.08 seconds for, well, I have it at 3.08. And then for the system, it's going to be this. Okay. So when you record, you can put down, and this is going to be what we would see from the user mode. So you can put down the real time. That's fine. Okay. All right. So we would put down the runtime for our program using multi-threads, right? Because when you uncomment it, basically we're going to execute that function call. So this is for multi-thread. Then what you're going to do is after you run that and put down the execution time, you're going to come back to the program. Now I'm just going to nano into the program, right? And what I want to do is I want to go all the way down to the function call. And I'm going to comment this out, right? Add a comment here, and then I'm going to uncomment the next one like this. I actually save a different file, so I don't like to, I wanted to see the difference. Because for demonstration purposes. So I'm just not going to save this one. I'm going to go ahead and show you my next file, which is I commented the multi-thread and I uncomment simple. So here you're going to call simple function, which is going to make our program sequential, not concurrent. Okay. So it's going to run in synchronous mode. So what you would see after you uncomment simple and comment multi-threaded, you would save the program, Control X, Y, enter, and then you would run it with the time. So Python 3, and for me, it would be 1. Okay, so we do see a little difference in the output for our execution time, right? And then it is also higher with the user. So on this, when we run it as a synchronous sequential program, what you have is you have a little bit higher. I want to say like maybe 30.3 second higher, roughly 0.38, 0.3. So you can do the math there. But even on the real time, you do see that, yeah, it's about 0.3 of a second higher. Okay. So for the sequential mode, it's gonna be slower compared to multi-threaded. Any question? So after we did that, we run the program again, we record our runtime, and we would do an analysis. Is that faster or slower? Right? Now on the IDE, let's look at it on the IDE. So if I go here and I comment this and then I uncomment simple, right? And then I'm going to go ahead and save this as V1. And then I'm going to run. Okay. So on the IDE, I'm using 8 core. It shows that I have 2.9 seconds. So is it going to be really consistent in how it's going to produce? So we saw that for the multi-thread, that was actually a little slower. Okay, in my case. Any question? Okay. So we see both version on the IDE, which I use Tawny, and then also in the Linux, where Linux we use the time command, and in IDE we use time it. Now we're going to modify it for the third time. So coming back here, I'm going to go ahead and nano into my next version so I can show you. So we simply just go down and we would comment out our multi-thread and simple, and we would uncomment multiprocess. And so now for our third iteration, that's going to be running the program as a multiprocesses program. So it's going to call on the multiprocess function. So once I've done that, I would then save my file, Control X, Y, and enter. And then I would use the time command in Linux to run my program. And know that I just saved a different version. So, okay, so we see here that I am on a 4-core for my Linux virtual machine, right, with 4 GB of RAM, which is minimal. I would have my real time is a lot less. So for multiprocesses, using multiprocesses, multi-threads per process, what I would have is I would have 1.43 or 1.44 seconds roughly for the real time. And then for the user time, it is slightly higher than that. Okay. So compare this to the sequential program, right? We save about 2 seconds, 2+ seconds. And then compare this to our multi-threaded program, we did shave off about 2 seconds. Now, coming back to, so after you have that, take a screenshot, right? Do the analysis, which one's slower and which one is faster. Is the sequential faster or slower? Is the multi-thread faster or slower than the multi-process? Now, note that we didn't really do much with the lock here, right? We simply use multiple ways to benchmark our program. It could be multi-thread or multi-processes. Now, if you want to implement the lock when you do the multi-threaded part, you simply declare your lock object, right? And then be able to use that lock object, like what we've seen in the example for our lecture, to be able to do that. Okay. So in the next part, what we're going to do for part B is we're going to benchmark HTTP requests. And I want to bring it back to this so that way you can see how that's done. Even though we did quite a bit of HTTP requests in the last week. Okay. So in this one, we're going to focus on threading and having it as multi-threads. Now we want to be able to use threads to submit a bunch of different requests to different web servers, right? So you can have a list of your URLs, and we would assign or have the workers, which are your threads, to be able to submit or use the GET method to access different websites. Okay. And so in the function for this, when you define the worker, you simply do a try and except. Remember, we talked about how we should handle exceptions. So we would say while true, try, and then we would have a variable called URL. And what it's going to do is going to pop off it's going to remove, right? So let's say that if I start with 25 URLs, Okay. When it submit that one URL, it's going to remove that from the list. So we need to have it pop off the list. Okay. And then for the accept, if it comes across index error, then it's going to break. Okay. And then for our function, we want to submit request.get, right? That's how you're going to be able to send that request to the server. And in this one, we are going to do a range of 10. So that means that we're going to have 10 threads. That's going to work on our list of URLs. So if this simple script, this is a way that we can automate, right? How you would be able to submit a bunch of different requests to different websites. So we would have a for range, and here we're going to pass 10 as we're going to create, right? We're going to use our 10 threads to be able to execute the get request for our URL. So we have an object called T, and this is going to be for us to instantiate for the thread. So here we create the thread, and our target is going to be our function, which is worker. And we would start them. Okay. So to write this file in your Linux machine, we would just go nano http threads.py. Okay. And we would start writing our, it's not too long. Then once we have that, we would then save, Control X, yes, enter. Then we run with time. So use the time command, Python 3, and then your file name. Recall that when you look at the program, we didn't really state what the URLs for, right? So, oops. Our list is empty, so that's why it's fairly quick anyway. So what you would see here is that when you run it, my output for my real time is 0.46 of a second. Now, how can I achieve this in an IDE? Okay. Here's part B. So let me clear this. So basically the program is the same. And then before my loop for the threads, because that's where you actually start your thread, right? And your thread is going to target the function. So you want to start your timer right before that. Okay, so think about the logic flow of your program. This is just a function definition. This is a container. The action really happens right here, right? So what I want is I want to start my timer there. So I would have a start time and then time it that default timer. So it's going to print out the system time. And then I'm going to loop, right? So I'm going to create thread, start my thread, and then each of my thread is going to work on, or it's going to execute this function. So as I start that, I want to time it, and then I want to print out my execution time. So simply it's like the same code as the last one. It's just I place it in a different area. Okay, so for the execution time, we would do a default timer, subtract start time. So on an 8-core in my IDE, yes, it is a lot faster, right? For even though we don't have anything in our list of URL. So what you would see is the core does make a huge difference, because that way we can use, multi-core for our threads. Any question? Okay, so I expect you to be able to show me how you could measure your execution time for your project, right? That was one of the elements that was stated in the project criteria, was to be able to test your program. So, okay. So after I run it, I would take a screen capture, and here on number 14, it tells you that these threads drop the GIL while waiting for each of the socket of operation that involved in fetching of the URL over HTTP. So they finish the work sooner than a single thread could. So that means that when you create threads for your HTTP, as when it connects, normally when you establish each of the socket, it would then tie that to a GIL, so it locks it. So the thread it drops the GIL, so that way it's going to be quicker to submit instead of running individual thread. Okay, because when you lock it, only going to be a single thread can access each socket at a time. So the question B said, what can you conclude about GIL in a multi-threaded program? Right, we see that if you use GIL in a multi-threaded program, you would need to force it to run one thread at a time until that GIL is released. Any question? Okay, so we saw how that's done both on Linux and on the IDE side. Now we're going to do the parallel. So what if we want to achieve simultaneous execution? We want to make sure that it is faster, or the task is finished sooner. And so when we scale that, we would scale it to parallel from multi-thread, right? You go from your sequential program, which is synchronous, into the asynchronous, which is multi-thread. And then after that, we would need to go into parallel programming. And so in parallel, it tells you here that GIL prohibits it in the scaling. So that means that you need to use multiprocesses. And when you use multiprocesses, you need to have more memory. So we would have to give more space in order to reduce time. And in a multi-core processor, that is good because we're capitalizing on the multi-cores. We talked about that before. So in this program for part C, we are going to fork 10 processes. Okay. And instead of doing one, we would make it 10. It's like when you're given a team of 10 people the one task, right? They're able to divide that up and be able to finish it sooner than giving that same task to only one person. So when we run it on the parallel on multiple cores, we are going to accomplish the task faster. Okay. Now, if we implemented the GIL, what you would see is that then it would take it away from really be able to execute now, because in multiprocesses, if you allocate one memory location per process, it's really 1-to-1, right? So would it be running faster with 10 threads compared to one thread, right? Only one thread can execute the Python at one time with GIL. Okay. So now when we fork the process, that's going to separate the GIL. And what you would have is that you are going to have multiple computational at once. So to implement parallel for the single process, you can use Jython or JPython or also IronPython. There are many different versions of Python. So as we know that CPython, and there are different types of Python that you can use. So these types of Python or those versions of Python can provide single process parallelism. Okay. And it is CPython compatible. So in this next example, right, or this next program, this must be done in Linux to really see the complete output. If you're only using it in IDE, you're going to have a traceback error. Okay, I'm going to show you exactly that. So if I put this program in my IDE and just to be done with, right, when I run it, right, I'm going to be able to print out my system time. But when it gets to the fork method, Windows system doesn't support it. Okay. You can also go to Python documentation and look up OS module and fork method, and it tells you about that. This is originated for Unix. Okay. If you use GitHub, you're also familiar with the fork mechanism on GitHub. Okay. So here, I'm going to have an attribute error. Okay. Because this method is really written for Linux, so you cannot run it on Windows. Windows will not be able to recognize that function. Okay, let's come back to our virtual machine now. We're gonna nano into, what did I call it now? Parallel GIL. And then you can write your program in using nano, or if you're using an IDE inside the Linux virtual machine like PyCharm. Okay, so for the program itself, you are importing OS. So this is the module. We talked about this before, and also sys. A lot of time when we use this, we want to print out like process information, like process ID, right? OS information, because on the low level, it should see it. We would have a list called nums, and we are going to have it loop using the for range loop to generate numbers. And we want to take that, we want to divide it up into groups, right, of numbers. So that way we would have different chunks. Okay. So I would take that and then cut it up into small chunks. Then I have a readers list. And then after that, I would have a while loop. So what we would do is we would be able to take our processes and these processes are going to be able to read, right, the values in the chunks. Okay. And we'll also have a writer, so that way it's going to pipe it. So as it read, it's going to append to the reader's list, right? We talked about reader writer this week. And with that, we would have an else statement. And we would initialize it as a subtotal. And we would loop it to increment. Okay, so we'll go to the next and the next and the next. So this is going to slow it down. Then we have a writer section. So as we go through it, this is a running sum, right? We initialize it at 0. So as it goes through, it's going to add the next index and the next index. So you have a running sum, and you're going to print it. Then for the writer, here you would have a writer, and you would take that and parse it into string because you want it in text, right? So we would need to encode it and parse it into string. And then we would do an exit. Then for the next part, we would have a total initialize. We would have a loop. So as it reads through, we would convert that, right? Parse it from the read, which is in string, and make it into integer so we can add it up. Okay. So when I read it and when I read it and append it to my reader's container, right, we want to make that into string and encode it. But when we save it, we want to save it as values, which is integer. So at this point, your subtotal here is going to be containing the values as integers. So we need to convert it back from our string. So we have to parse it back into the integer and use the decode. Okay. And also it's going to give you the total, which is also a running sum. And then print. So ultimately, we use our process to be able to handle, right, chunks of the value. And this is how, when you have a very large set of data, you can section it and write a multiprocesses program to be able to target, right, those divisions or those partitions of your data, instead of just looping through sequentially, and that might take forever. What if you have millions or billions, right? So what we can do is we can chunk it up, and then we can write we can create multiprocesses to be able to handle it. Okay. And in this one, you don't really see, right? This is really for parallel. So we capitalize on the OS and the sys module. So you don't have to write, like, you don't have to instantiate the process objects and then be able to set up your workers and all of that. So you simply would use it with the fork here. So it automatically take your operating system process and divide it up into 10 and be able to execute. Okay. So this is another way that you can do it using those modules. Okay. So we talked about part C not being on the IDE. Now we would run it in our Linux system. So after you write your program, Control X, yes, enter to save. Then we would time it. So use the time command in Python 3 to run it. Okay, so we have the subtotal prints, right? And then here our real time is 0.15 seconds. And I'm on a 4-core. User and your system time. So in this case, you see that the user is less, right? And that is because it's using the existing, or it's using the operating system processes, right? So what you would have is you don't need to create any kind of object to be able to handle that. You just use the resource that provided in your operating system, as you will fork the processes that way. Okay, so natively it's able to already instantiate the process for you, so you don't have to create it in your code. All right. So when we ran it, take a screenshot. And when you look at your code, how is it implemented? You would see that here. So it was added to read your data, right? And so when you fork it, it divides up your processes to the chunk of your data. So that was implemented in the while loop here. And then here. And that was using the OS module. Okay. Okay. Now CIS allows us to use the IO stuff. Okay, so that, and along with the OS, so you were able to read and write with the CIS. Okay, then you are going to answer, what can you conclude about GIL and parallelism? And in that, what you see is that, remember, before this exercise, it talks about how multiprocess needs their individual memory location. And we purposely chunk this up so that way each of the process can access its own location or container of data. So that's why you need to chunk it. Otherwise, right, we don't want to have multiprocess program that's accessing shared data. So because in some cases you might have different values that generate different subtotals, so you want to be able to divide it up so each of the process would have its own chunk. And that was implemented here and up here. Any question? Okay, so with that, you should be able to answer GIL. And then I want to finish, so I can just say shut down. Yeah. Okay. Then let's see. That's pretty much covered the lab for today. And then you just need to submit your screen capture, lab questions, and answer by Sunday. A little behind on grading right this week because I got a little bit more busy schedule as far as meetings goes, but I will try to catch up tomorrow and Saturday. So you should have your updated grade. I want to touch on, there were questions about project example. I will clean up my GitHub repository a little bit. So I pull some of the projects and I will add more. So when you click on the project module on the last page, you will see this. And then when you click this, you should be able to go to my GitHub repo like this. So there are 3 projects that I put on here, and I will try to clean this up and put it into like source code folder and stuff like that later on. But these are the top project that was submitted for this particular class. One did speech to text using Python. Okay, there's asynchronous multiprocess and then also benchmarking and tests. So you can take a look at the program. So the speech to text, this was submitted as 4 files. And then I think there is the documentation for it. So when you click on this, I just uploaded the file so you can look at what the student submitted. Okay, and then the flow chart. Then, so there was some interest. This individual expressed a lot of interest in like speech recognition. He was working on a project prior to my class. When he took my non-credit class, I think he also did like IoT Python programming, which I teach in spring. So he did a similar project there. So he took it and he improved it. So that was what was turned in for this class. Then there is a zip file. This person have high interest in cybersecurity, and this student created a network scanner using she used a little bit of the open source code from another developer, and she did ask my permission prior to submitting the project. And I looked at the code and I looked at what she produced, and it seems to be okay. So this is her final project, and the documentation of that is this one. Okay, so I will do better in putting it into subdirectory. So it talks about like what it's looking at, what kind of things, what kind of library that would be used. So Scapy, I explained this in my networking class for Python programming and also cybersecurity ones. So she also took that, so that's why she's using it for this. But tk-enter was covered in 30A, matplotlib a little bit in this class and also in another class. So what you see is the design, and she even actually integrated the interface. So she worked on having like buttons. So her goal was to make a scanner, right? That was focused on like denial of service attack like this, and then be able to have like plot the data like an analysis. So she can take this and improve it. I really like it. So eventually be able to add like a little window to be able to show the plot instead of clicking the button. So you can input an IP address and be able to scan it and then output some form of report along with plotting. And that's, in security world, this saves us a lot of time. And because people who make tools like this and share it, right, eventually it will become better as the community would improve it through open source network. Okay, so she did some tests, and so as you can see that, right? And in technology, I'm okay with you having stem your idea from another program, but what you don't want to do is to take that program and then, call it your own, right? You can use the idea and then be able to integrate that into your project. So, just to build or improve an existing program is also good. But if you want to clear it with me first, that's fine. So instead of like having to deal with plagiarism right down the line. Long ago for another class, I actually did not pass 2 students who turn in the exact project from with one another, and it's also an exact project from someone else that's not at MVC. So I want to make sure that we're clear that we don't want to submit other people's code. And also, you know, at the university level, that's a definite expel. So you don't want to work hard on your courses and then not be able to get the credit or finish the program or the degree. So, okay. Ethical reasons, right? Let's go back. And then one of the other program was an order system. And the documentation for that is, it shows here documentation 1, and then you can download it and take a look. But for the file that was submitted was the order prepare.py here. And so you can take a look at the code on how observables were implemented, threads were implemented. This student, she is a junior developer now at one of the organizations. So you can see how her work is. So it is like a boba tea or a coffee, a tea place order system. So if you're thinking of doing something similar to this, like a restaurant order, stuff like that, you can take a look at this. And I think any application can use performance boost, right? It doesn't have to be super fancy, like something web related or something network related. If you're not familiar with that area, but you have some interest in other things like game or an application that you previously worked on and you want to improve, you can definitely revisit your code and then say, hey, you know what, I can add in different section and modify my program and make it concurrent, you know, or implemented the concept for this class. And that's the whole purpose. Okay. So I will try to reorganize this so they can kind of go together. So I'll create sub-projects. I just didn't have time to tear it through and then create the README for it, but I will work on it this weekend. But it is now at least available. I'm sorry I couldn't have it available for you on Tuesday. It's just my calendar been kind of crazy lately. So, but anyway, it's there now. Okay. So you will be able to see it. And then I'll add other projects on there. I got to look at it again to make sure that they're good. It's been a year, so sometimes I forget how good they are. All right, let me stop recording.